Well, Brent, Qindan, Michael, thank you very much for those very wonderful talks, sort of explaining sort of the environments in which you're trying to understand data and apply it for sort of understanding how ice is impacting the world, how pollution is impacting the world, and sort of how we can sort of better make use of autonomous systems in our water systems. So I'm struck, I think one of the things as I'm looking at all these different talks, I'm struck by the diversity in the scale of the data. Yeah, so it's coming at you in different time scales, different spatial scales. You're collecting it from satellites, from underwater vehicles, from autonomous air vehicles. How do you visualize and interact with that data? And are there opportunities to interact with it and visualize it in novel ways? And in particular, I'm thinking, sort of AR and VR gaming technologies. I don't know if you've used those things, but like maybe you can just tell us a little bit about the struggles with, as you collect this rich multimodal data, like how does it come down to sort of really the data engineering and the data plumbing to sort of make use of it and apply it to your various spaces? So I mean, I guess we'll just start going through in the order of the talks here, if that.
Sure. Yeah, I'm happy to jump in. So the way we visualize it now, I guess the way we make use of data now is kind of twofold, right? There's the straight visualization, similar to the maps that we show in the talks, and then of course we can set up movies similar to the ones that we were talking about to deal with time series of data. That works out okay for a lot of the things that we're working with right now, because our data, a lot of the data that we work with is still two-dimensional, and two-dimensional occasionally resolved in time. And so, simple sort of 2D figures, movies of changes over time and so forth, works okay from a data visualization perspective. The other side of how we interact with the data, of course, is data assimilation methods. So we assimilate data into models of various types, or we're basically trying to use data in order to infer physical quantities. So it's often the case that what we really want to know are things that we can't directly measure, and so we're measuring things that we can measure, and then we're inferring the things that we want to know using some combination of data and models. And so there's a lot, underlies this notion of data assimilation, whether it's straightforward inferences from relatively simple models, or much more sophisticated data assimilation methods that are similar to what we do for weather forecasting and so forth, where we're taking a complex model and we're kind of guiding it along, essentially, by working with and ingesting data kind of on a case-by-case basis. But as we move forward and as we get better quality data sets, in particular as we are able to improve the temporal resolution of our data, which is the main hurdle that we're working to overcome at the moment, then we're going to have to start thinking more creatively about how we interact with and visualize data. Not only because the size of the data sets themselves is going to explode, but the dimensionality of the data is going to improve as well. So we're going to start to move toward a future where we have data that is resolved in all three spatial dimensions as well as in time. And so we're going to need to start to develop better tools to both interact with as well as assimilate the data into models to gain insight.
Oh, wonderful. Awesome. Definitely some interesting opportunities there.
Yeah. It's an exciting new future.
Yeah, I can just start with my satellite data sets. For the air pollution or air quality of the satellite, the raw signals that you receive from the satellite, it's very hard to visualize because that's basically the radiation, and you need to go through the multiple steps of the calculation and retrieval, like algorithm development, in order to get a global map of the concentration that you are, the chemical components that you are interested, for example, nitrogen dioxide. And what we get eventually will be the global map of different air pollutants as a daily scale for the current satellite products. And there are multiple levels of the products, including raw data, L2 products, L3 products, and L5 products. And right now, on the website like NOAA and NASA, they already provide a very good visualization tool that you can just go to the website and select the dates that you are interested, and it will pull out a map of the pollutant from the satellite observations for you. So I think that would be very amazing, because even you are not in atmospheric science research, you can still click into that website, look at the map, maybe zoom into the region that you are interested in to say, okay, what are the extent of the pollution it is at that moment. So yeah, I would say that's the best tool of the visualization for the satellite products in our community so far. And on the other hand, we are intensely using the model simulations. And as Brent just said, model simulations will encounter a lot of issues with heavy computational expensive, very large data size, because already your data will be like 3-dimensional and you will have very tight time steps. And that's why in my project, I intended to use machine learning as an emulator of this climate model, because running a machine learning model will be less computational intensive. And then I can just use machine learning to generate as much of the data sets that I need at that moment. And I don't need to like go back and rerun this heavy, computationally heavy model simulation again. And for the visualization of that part, I would say visualizing machine learning model or visualizing model simulations are all about the same, that you are using all the existing like packages of tools. But I hope in the future, maybe we can create some real-time visualization tool for the machine learning outputs or the model simulation outputs. Then we don't need to store this big amount of data at somewhere and then pull this data at the point that you want to do visualization and then go through a long time to do the visualization. So I think that would be one of the future goals, and I hope like people from multiple fields can work on that.
So it's an interactive visualization during the process.
Like the real time, that if you want some like air pollution map, you can just pull it right away, like in seconds. I would think that would be very amazing.
Very good, thank you.
Yeah.
Michael.
Yeah, so there's two types of data that are commonly associated with our robots. When we deploy autonomy on our robots, it's usually in service of a stakeholder who is using the robot to collect data in the environment, something about the underwater or surface or environment, et cetera. And that really varies between robot users, depending on what the vehicle is and what they're trying to do. The common thread for us is the autonomy side. So how did the vehicles maneuver relative to each other? Were they safe? Did they have near collisions? Things like that. That's the data that we care about across all projects. And it comes in two forms as well. There's getting your data off your robots that are actually in the field. And everything we do in the field, we try to do 1,000 times or more in simulation, and in some cases, much more than that. So if we're going to run 100,000 simulations, we have to be careful about how much data we store with each one of those. And as we get better with our autonomy algorithms, it may be the case that 1 out of 10,000 missions has an event of interest. So we struggle to, and we've spent a lot of time investing in how we scrape data off of our vehicles and autonomously look for events of interest, so that as that data is being archived, we look for events of interest and we keep rich data around that events of interest, and we keep very thin data for the rest of the data sets. And so for us, it's a lot of custom engineering to automate the getting of the data off of the robots. We had our class this week, MIT 2680. It's a marine autonomy sensing and communication. And the final project was students fielding 4 robots, and they have a 15-minute time slot. And as soon as they come off the water, they put a swap computers, and the next team goes. So getting data off of those vehicles in that time frame has to happen within like 5 minutes of the end of the mission when the vehicle is coming off. And so we've automated that process. So we have the full archive of all the student competitions from that, but it was not an easy process. And we strive to do that for other projects with our stakeholders, where a lot of times we engage with users who have an amazing vehicle and they come to MIT for help putting the autonomy system on it. But they may be located in Brooklyn or Maine or Maryland, wherever the robot company needs to be. So what we strive to do is, as we're working with these vehicles, have missions that are completed to get the data off of these vehicles archived and sent an email out to, or some other form of a notification out to the stakeholders that a mission just happened, and they can go look at the data set. And that turnaround time, that pipeline that turnaround time of experiment data analysis, getting as many people to look at it as possible and get their opinions before we go out next is really critical. Because if we can do that on a daily basis, go out 5 times in 1 week, where in the afternoon everyone's looking at the data from the morning, that's incredibly valuable in terms of how we approach our research.
Yeah, very interesting. So I picked up a couple of themes. I do want to encourage the audience, please do submit on the Q&A. I'm going to pick up on a theme of sort of machine learning and also sort of the data pipeline here for the next questions, but I do want to take some questions from the audience, so please do submit. But first, Qindan, you made a comment about machine learning. And certainly you can't do anything right now without people talking about the power and benefit of machine learning and say, hey, it's all about the data. There's a lot of value, a lot of information in our data. I guess the question that I want to pose is, how important is it sort of incorporate, where are you in sort of the balancing of pure data interpretation, sort of trying to learn sort of blind from data versus sort of using the physics and contextual knowledge of where that data is coming from? And I think personally, I get the sense that a lot of people say, hey, we're just going to get a lot more data. We're just going to learn everything we need to know from the data and not need to know anymore as much about the context or the physics or the understanding. And so I do see that as a challenge. I'd just like to pose that question to you, and maybe we'll start, Qindan, you inspired me to ask the question about machine learning, and we can go then Michael. Then
Sure. I think the application of machine learning is becoming a cutting-edge topic in almost every research community, as well as in atmospheric science. And there being a boost of the studies that are using machine learning in environmental science, and both to study the air pollution at the urban scale or studying the climate-related questions at the global scale. But on the other hand, there do have concerns about, okay, you are only learning the results from the data. It's mainly data-driven. So you are basically ignoring all the physics and chemistry and the whole community have been working on for decades to get it improved. But in terms, for me as a person who is actually using machine learning in atmospheric science community, I've been thinking about these questions a lot. And I do think that it's not just to like extreme decision that you purely use physics and chemistry to do the question, or you purely use the data-driven approaches. And at some point, you can combine these together. I can pose two examples. The first example will be, okay, for the machine learning, in terms of the input feature selection, you do need your understanding of the science behind to get the optimal selection of the input features. In my case, all the input features are selected based on my understanding of the OH chemistry. And in other studies that I've been heard of, it's all about like input features. We know that these parameters are physically or chemically linked to the prediction that you need. So there will be one combination. And the second combination will be we can change the loss function that we use in the machine learning model and apply our physical knowledge to constrain the loss function. In that case, you are actually embedding some of the physical or chemical understanding into these machine learning model frameworks. So even though this machine learning prediction is still learned by the data, it somehow also complying with the chemical rules or physical rules set behind.
Very good, thank you. I like that. Michael.
Okay, so in marine robots, our typical users, which can range from science community to industry to DoD, are very conservative by nature, especially since we're deploying vehicles that could be worth a lot of money in the ocean environment. So for the most part, when it comes to the autonomy system, the user or the operator really wants to know what the vehicle is doing and why, and wants it to be explained, and is not usually comfortable with a black box solution which they can't see the reasoning behind it. That being said, our autonomy system is comprised of a bunch of interplaying modules that perform a multi-objective optimization problem every iteration of the control loop. So those problems, multi-objective optimization problems, by nature have weights, and those weights can be tuned or learned. So I think there's a lot of opportunity for machine learning to be applied at that level of the process. And some of our work, admittedly more in the education and research environment, we create competitions, adversarial competitions, where teams are using strategies to compete against other teams. It's a bit contrived. It's more to really bring out the intensity of the students who are doing this. But nevertheless, there's a strong case to be made for using machine learning. Once we have those simulated competitions up in the thousands and teams can learn why they were beaten by another team, there's a strong case to be made for, and I know students will be applying machine learning to that. But in terms of our core autonomy, we're still at the very heart of it, very conservative in the sense that all of our users across the board want to know what the vehicle is doing, why. And it's okay if a sensor system is using a machine learning black box approach, or some of the other subcomponents. But when it comes to a vehicle that's out in the water, if it's going to be trusted, the user needs to know what it's doing and why it's doing it, what it plans to do next.
Very good, thank you.
Yeah, for us, standard breakdown, interpolation versus extrapolation comes into play, right? And so what we're very interested in doing is projecting what sea levels will be, and that is projecting sort of future scenarios that are outside of any calibration state that we have, right? Climate is warming. There's more energy available to us than any of our data sets have, that can cover. And so we're naturally, the main problem that we're interested in is an extrapolation problem. And so machine learning is just not useful for that in many ways. But it is a powerful tool that we can think about in learning the problems that are related to interpolation. And so we can infer a lot from these very large data sets, as you was talking about before, developing emulators and so forth, and taking advantage of the computational advantage that machine learning gives to us. But we do this, and there's a lot of work that goes on in this, sort of within this kind of physics-informed framework that was discussed before. So there are aspects of the physics, for at least our problem, that we do really understand quite well. A lot of it's 19th century physics, right? And so it's kind of, we can push forward on these things, and we can force our machine learning algorithms to respect that physics by changing the objective function or the cost function within our framework, and have this physics-informed neural networks, physics-informed machine learning, and so forth that push forward, that allow us to very efficiently infer physical quantities, physical parameterizations, and so forth within the system, kind of more down in I don't want to say the details of the system, but focusing the power of machine learning and the data that we have to learn the aspects of the system that we don't feel like we understand, and then respect the knowledge that we have available to us about the physical process of the system. And this ends up working very well. Again, we take advantage of the incredible computational efficiency that we can get from these tools. So we can learn these things. We can learn uncertainties, very importantly, around a lot of for example, the quantities that we try to infer, the calibrations that we make. We're able to now have kind of end-to-end uncertainties that respect the errors and the observations that we make, all the way down to sort of understanding the errors that we pick up due to simplifications in the models and whatnot. And then we're actually able to output a kind of a full kind of, call it a posterior distribution, the probability of a calibration parameter, for example, taking on any particular value in a way that we've never been able to do before, because it's just so much cheaper now with these tools that we have available to us. So that's how we're really using machine learning as a field here at MIT and so forth to work on the problem of projection.
Mm-hmm. Very good. So time goes by fast. We have a couple questions here from the audience, but they were asking how to get in contact with you. So actually I want to sort of build on that. We want the audience to reach out to you. What would be the exciting thing that you would like to collaborate with? What would be, if somebody reached out to you and said, hey, Michael, Brent, Qindan, I would love to do this with you, what would that thing be that you would love to have a collaborator working with you on? Michael, we'll start with you.
Okay, so real quick, our best collaborations are people who have built really incredible robots and have gotten to the point where they have them joysticked, or they can go from point to point in the world, and they want to make them more autonomous, they want to make them work together, and they don't want to start from scratch and write in the autonomy software. So we have an open source software project called moosevp.org. It's been online since 2006. It's got 40 work years of development effort. It's used around the world, and we love working with people who have robots that want to port this software and do something with it and not reinvent those 40 work years of effort.
Okay, so bring your robots. Okay, Qindan?
It's a hard question. I'm basically open to anything, right? But I'm mostly excited about the collaboration across different fields. So right now we are doing like air pollution, we are doing climate science, but I'm more excited to see people outside of this community that can reach out to us, and then we can seek for some very inspiring ideas that can work across together.
Multimodal, multi-physics, multi-domain collaboration.
Exactly. We have a lot of data here, so anyone is interested in our data set, feel free to come and we can share our data.
Thank you. And Brent?
Yeah, similar kind of idea. Yeah, I'm always open to interesting ideas, particularly ideas that have been well developed in other fields that we can transport over and be useful to the field that I'm interested in. And so this for us involves a whole range of things, from sensing technology. As mentioned in the talk, we're working with folks in AeroAstro and other places to build autonomous drones that can fly for months at a time, collecting observations in a way that we've never been able to collect them before. And what we're really interested in is understanding, how ice fractures, how ice slides along its bed, how the ocean is interacting with the ice in places that we cannot directly observe, right? And so interesting ideas about how we do a better job of making the measurements that we can make within reasonable budgets and so forth, and respecting the fact that the environment that we work in is very hostile to most anything that we have out there. And then working to better understand how do we infer the quantities and what are kind of the physical processes that we should really be focused on to better understand how the ice sheets are going to evolve, how they're going to respond to changes in climate. So anything related to material science, civil engineering, because the interaction of the ice and the bed is all about saturated granular materials, which is a rich and fascinating environment on its own, as well as sensing technology, both in terms of vehicles to give us better temporal resolution as well as instruments and so forth.
Okay, with that, thank you very much for your time and the questions. Please reach out. We'll make sure everybody's available. And next, we're going to hear from some students in some short talks. And then we'll also, in between those student talks, we'll do a live demo here in the Immersion Lab, embedding in the ambient sensing that's around us. So stay tuned. Thank you. Thank you.
Thanks.
Thank you.
Yeah.